Okay, another interesting effect that comes from the interface is the Laplace pressure. And this is the fact that small spherical droplets of phase beta in phase alpha will have a pressure inside the drop that is greater than the pressure outside. So how can we see that from the thermodynamics? So if we consider the total thermodynamics of the system, so let's consider a system that is adiabatic, that is S is constant at equilibrium. So du equals 0. So in that case, we have du is equal to T ds minus P alpha v dv alpha minus P beta dv beta. So here I'm dividing the phase into two pure phases, right? Plus gamma dA plus sum over I mu I dni. Okay, so at constant S, this is 0. In equilibrium, this is 0. And then at fixed volume, we know that dv alpha has to equal minus dv beta, right? And we also know that at constant, or because of mass conservation, dni in this situation is 0. So as a result, we end up with a much simpler version of this equation, which is just that 0 is equal to P alpha minus P beta dV beta plus gamma dA. And if we assume a spherical droplet, A is equal to 4 pi r squared, V is equal to 4/3 pi r cubed, and when we take what we can see in this equation is that P alpha minus P beta must be equal to gamma dA dV beta, where V beta is the size of the drop. And if we take that derivative, which you can do, I'll trust that you're able to do that math, what you get is that delta P is equal to 2 gamma over R. So this is our delta P is 2 gamma over R. And that's known as the Laplace pressure, and we can see it varies with radius. As the radius gets smaller, the difference in pressure between the drop inside the droplet and outside the droplet gets bigger and bigger. So we can see that as a consequence, consequently, the vapor pressure of small droplets is greater than that of big droplets. So now let's think about the thermodynamic equations that apply inside and outside the droplet. So we have S alpha dt minus V alpha dP alpha plus N alpha d mu alpha equals 0. We have S beta dt minus V beta dP, right? So here we're writing down our Gibbs-Duhem equations inside and outside the droplet. And if we consider variation in mu, right? Consider varying or consider what happens when the radius and the temperature are constant. We know that because inside and outside the droplet we have to have some equilibrium, right? So mu alpha has to equal mu beta. So as a result, what we get is that, and here I'm going to define omega as the volume per unit mole. So this is the molar volume. So now I can write this expression. So at constant temperature, these are going to go to 0, right? And I end up getting that the molar volume of alpha, or minus the molar volume of alpha dp, plus d mu is equal to 0, and minus the molar volume of beta dp, so this is dp alpha, dp beta, plus d mu is equal to 0, right? And so I can put these together and I get dp beta minus dp alpha is equal to, be more clear. So I can set these equal to each other, right? So I have d mu is equal to omega alpha dp alpha, which is also equal to omega beta dp beta. So, and we know that dp beta minus dp alpha from our Laplace pressure on the previous page is equal to d2 gamma over r. And now we can write down dp alpha in terms of dp beta. So I can get an expression that 1 minus omega beta over omega alpha dp beta is equal to d2 gamma over r. Okay, so if we further assume that beta is a liquid, so it's a liquid droplet, and alpha is a vapor, then omega alpha is much greater than omega beta, right? And in that limit, we're going to get dp beta is just equal to d2 gamma over r, right? And since we now can relate dp beta to the chemical potential, we can write down an expression for the chemical potential. D mu is equal to omega beta times dp beta, right? Or omega beta times d2 gamma over r. So mu as a function of r is going to be equal to mu for the infinite size drop, because that'll be the flat surface, plus 2 gamma omega beta over r. And this is what's known as the Gibbs-Thompson equation. And it gives us the how the chemical potential of the drop depends on the radius of the drop. So we can see that the chemical potential is raised or lowered relative to a flat surface by an amount proportional to the radius of curvature. The consequence of this is that if you have a system with small droplets, those small droplets are going to have a different vapor pressure than large droplets, and the smaller droplets will be disfavored relative to large droplets, and so that'll lead to coarsening, or in a conserved system to what's called Ostwald ripening. Favors large droplets, so we get coarsening, or Ostwald ripening. All comes from this basic physics.